Hello and welcome to Nomenclature, Roman or stock system. This is the third system of nomenclature after binary and ternary. We still have two left. We have Greek and acid nomenclature. You may consider polyatomic ion nomenclature as one of the classes, but either case, Greek and acid are left after this. Let's begin by identifying the 11 steps to name a chemical formula given the Roman system. The Roman system is used for compound salts that have as the positive component a D transitional element or a heavy P element. So let's begin. 1. Identify the charge of the negative component, the negative ion, sorry. This is constant and can be looked up on a periodic table or the polyatomic ion reference sheet. Number 2, draw a box around the negative component. 3, multiply the charge of the negative component by its subscript. 4, just outside the negative component box. Number 5, draw a box around the positive component. Number 6, just outside the positive component box, place the equal and opposite charge relative to the negative total charge. Number 7, draw the total positive charge by its subscript. 8, problem. Number 9, convert the number to a corresponding Roman numeral. Number 10, write the name of the compound using the rule systems of nomenclature. And number 11, place the Roman numeral after the name of the positive component. Now, you're going to want to write these rules down on your sheet, on your reference sheet, so you can take it into the unit test on nomenclature. Now, let's begin by looking at an example using these 11 steps to answer the question, what is the chemical name of a chemical formula? Here is a chemical formula. Looks like it's the same chemical formula, just some subscripts in there. Well, we have FeO and Fe2O3. Now, we have to identify the oxidation number of the positive component. And to do that, we're going to work backwards. So you want to identify the charge of the negative component. This is constant and can be looked up on the periodic table or the polyatomic ion sheet. And you know that oxygen from the periodic table is -2 in both cases. This is constant and will never change. And you can always depend on that. Now we want to draw a box around the negative component. Sounds like a very simple exercise, and it really is. But what it does is it kind of separates for yourselves the problem into a negative and a positive component. Next, you want to multiply the charge of the negative component by its subscript. In the case of FeO, where you have one oxygen, it'll be 1 times -2, and Fe2O3, it'll be 3 times -2, which is -6. Now, you want to, just outside the negative component box, place the total negative charge. Again, for FeO, that'll be -2, and for Fe2O3, it'll be -6. Now, the next, you'll be able to see where some symmetry lies in this whole procedure. Draw a box around the positive component. So now you have FeO with a -2 charge on the negative component and Fe2O3 with a -6 charge on the negative component. You want to, just outside the positive component box, place the equal and opposite charge relative to the negative total charge. So in the case of FeO, that'll be +2. And in the case of Fe2O3, that'll be +6. So now you see the symmetry. Now you want to take the total charge, divide the total positive charge by its subscript. Total charge of the positive component divided by the number of ions contributing to that charge, and so that will give you the oxidation charge of the positive component. And in the case of FeO, that's going to be plus 2 over 1, which is 2, and then plus 6 divided by 2 equals 3 for the Fe2O3. So now you've written the answer to the division problem. Now you want to convert the number to a corresponding Roman numeral. And in the case of 2, it's capital I, that's the Roman numeral 2. And for 3, the Roman numeral will be capital I, and that will be the Roman numeral 3. Well, you want to write the name of the positive of the compound using the rules learned in the binary and ternary systems of nomenclature. So for each case, it's going to be iron oxide. The name of the positive component, the name of the negative component. This time it's a single element, and it's going to be IDE. Now you want to take the Roman numeral and place it after the name of the positive component. So the way you read this is iron 2 oxide and iron 3 oxide. So those are the names of those two compounds that we started with. The names are iron 2 oxide for FeO and iron 3 oxide for Fe2O3. The color of iron 2 is brown. The color of iron 3 is bright red. So there are differences in these two irons, classic differences in these two irons. Now, the following slides have practice converting formulas to names. Try to name each formula before the name is uncovered. Now, we'll start slow and then we will speed it up so it's only 2 seconds per slide. So this particular formula to name, again, remember to turn off the video, put it on pause to see if you can come up with some of these names. So the first one is Fe3PO3 with a 2. So it would be Fe, the formula. Now you want to convert it, and it's going to be iron 2 phosphate. The next one is going to be nickel 3 iodate, etc. So good luck. Keep going. Remember to put it on pause when you feel that you can do this by yourself. Be back in a minute. Okay, so how did you do? So what we'll do now is we will look at how to convert a name to a formula. How to convert a name to a formula. The first step, and there is not as many steps with this as there was with converting a formula to a name. But the first step is to remember that the Roman numeral is the oxidation number of the positive component, or the metal. So in this case, if you have something like iron 2-phosphate, the iron is +2. The iron is +2. So you would write the formula from iron 2-phosphate to begin with as Fe +2. The formula of the negative component is always constant and can be readily looked up. In this case, phosphate, PO4, -3 charge. Now, you know that these are readily looked up using the periodic table or the polyatomic ion sheet. Now, in the periodic table, you know that groups 1 and 2 are +1, +2 respectively. 13 is +3. 14 is ± 4. 15 is -3. 16 is -2. And 17 is -1. And then you have the polyatomic ion sheet that you can use as well. Now we want to use the techniques from binary and ternary nomenclature to write the formula of the neutral particle. Now, you remember the neutral particle, you have the reason, for instance, iron reacts is because it goes from its ground state, where it has an equal number of protons and neutrons, then it reacts and it forms a charge to be stable. But it's not completely stable until it can be part of a particle that's neutral. It can be part of a particle that's neutral. And in this case, it's going to combine with phosphate. But how is it going to combine with phosphate? Well, you could exchange the oxidation numbers for the corresponding subscripts. That's one way of doing it. You can also think 2 and 3 is 6. That's the LCM. Well, how do I get +2? How do I get 6? Well, I multiply it by 3. How does -3 become 6? I multiply it by 2. So I can find the subscripts that way. I can do the crisscross way. However, the problem with the crisscross way is if you have even oxidation numbers, you're going to have to do some reduction. So for instance, if you had 2 and 1, or sorry, 2 and 2, +2 -2, it would be 1 to 1. Or 4 and 2 would be 2 to 1. So in this case, it's going to be Fe3, PO42. You just exchange the oxidation numbers of each of the elements for the opposite elements, the opposite components subscript. So here we have the iron 2 phosphate is Fe2, PO4 2. Now, I want to do some practice. It'll be similar to what we just did in terms of practice, and that is we're going to convert names to formulas given a large worksheet. And I'll start off slow, and then I will speed it up. And the following slides have practice converting names to formulas. Try to write each formula before the name is uncovered. Remember to turn the player, turn the YouTube on pause, and see if you can name the substance. I'll go slow at first, and then again it will be 2 seconds a slide. It'll go very quickly. So let's begin by converting name to formula. We're going to mix up the negative components as polyatomic ions or individual ions, where you answer it as IDE, odd. Okay, so here's the worksheet, name to formula, and I will uncover each one individually before we turn it on and we go real fast. So the positive component on the first one is going to be iron 2. Remember, that's going to be Fe with a +2 charge, and phosphate PO4. And also you can look that up, and that's a -3 charge. So the first one looks like this: Fe +2 PO4 -3, and then that turns into simply exchanging the oxidation numbers. That turns into Fe3PO4 2. Okay, let's begin. Okay, and they're off. How many can you answer quickly? I'm going to uncover all the positive components, and then we'll start with the rest of the phosphates. Okay, remember to turn off when you can. See if you can write the formulas quickly, and then when you get comfortable with this, put it on pause and see how many you can do yourself. Okay, be right back. Okay, we're about ready to go on the last stretch. This is sulfide. This is actually the only negative individual ion. Sulfur would be sulfide, oxygen, oxide, chloride, fluoride, bromide, iodide, etc. So we're almost finished, and you'll be having your quizzes on this shortly. Make sure you look at this YouTube video again and see how much you learned between the first and second time that you watched the video. Okay, remember, any notes taken by hand on this video can be used on any tests given on nomenclature. Tests given on nomenclature, not quizzes, but tests. So good luck, and I hope you enjoyed it. Goodbye.